Hello, friends. Excited to spend a little bit of time with you today. Let's go ahead and share the screen and we will get started. All right. So what I wanted to talk to you about today is section 7.2. And so for section 7.2, we're going to have 19, we're going to have 20, and we're going to have 21. So this is probability and fun stuff like this. And I've got to admit, I really am enjoying this. Okay, so 7.2. It says 18, 20, and 21 assume that a year has 366 days and all birthdays are equally likely. Okay, so that's important. 366 days. Now then, exercise 19, it's equally likely that a person is born in any given month of the year. Okay, so let's read these questions. 19. What's the probability that two people chosen at random are born during the same month of the year? Okay, so we've got two people at random. Now, do they give us any hints on how we can assume that they're going to be in the same month? Oh, okay. Exercise 19, assume it's equally likely that a person is born in any given month of the year. Okay, so there's 12 months in a year. All right. So we're going to have to, let's hop in the, well, okay. I'm going to go ahead and I'm going to change my camera here. Let's see if we can hop in. There's 12 months and we want two people born in the same month. Okay, so let's hop over here to our PDF. There we go. And here's our text. And this is probability theory. Okay. Let's look for some examples that are close. Heads or tails when a fair coin is clipped. That's not as helpful. N elements. Suppose that S is a set with N elements, 12 months. The uniform distribution assigns a probability of 1 over N to each element of S. So the probability of S equals 1 over N. Cool. So the probability of an event E is the sum of probabilities of the outcomes in E. That is, I don't think that's helpful. Okay, probability of a family with two children has two boys, given they have at least one boy. Well, we don't have anything that's been given yet. Okay, we've got independent events. Okay, E and F are independent. So the probability of E and the probability of F are independent. So the probability of and so this is for part A. All right. So 7.2, question 19, part A. My first guess is 1. Oh, no. Oh, okay. So let's reread the question. I think I missed a piece of information there. What is the probability that two people are chosen at random are born during the same month? Okay, so I think the part that I missed here, the reason I did that wrong, the first person is born in a month. What's the probability that the second person is born in the same one as the first one? Well, the probability of the person being born in a month is 1. The second person being born in the same month is 1 over 12. So it's not 144. It should be 1 out of 12. Okay. Now, the second question, what's the probability that in a group of n people, so this is 17b or 19b, we have n people. And it says, what's the probability that a group of n people chosen at random, 2 people born in the same month of a year? So the first one, we're just choosing 2 people. And so the probability of the first person being born in a month was 1. And then the probability of the second one, which is independent, is 1/12. Well, now we're choosing more than 2. This is 1 person. And now, instead of 1 over here, we're going to have n minus 1. So I think it's going to be n minus 1 over 12. Let's go back and I'll go ahead and share my screen. Okay. So for part A, it was 1 over 2. Oh, nope, I was wrong. So the way they're doing the math on part B is they're saying it's going to be 1, which is the probability of the first person, minus, this is the probability that the second person is not born in the same month, or the third person also born in a different month than the first one. And then okay, and I'll be up forthright. I don't necessarily understand all that. All I understand for sure is my first assumption was wrong. Okay, so for part C, 19C, the number is going to be 5. All right, so let's go find out what question 19C is asking. It says, how many people chosen at random are needed to make sure that the probability make the probability greater than 1/2 that there are at least 2 people born in the same month of the year? So if we want probability to be 1/2, what is n? Okay, now I do remember them talking about this in the PDF. Go back up to the top of it. Okay. Probability assigned to outcome to heads. Random string. Heads and tails flip again. Ah, the birthday problem. Here we go. Smallest number of people you need. Two of them have the same. All right, so 366 days a year. We're not quite doing that. We're doing 12. So we have n equals 12. At least two of the n people in the room have the same birth month. We calculate the probability of n that these people all have different birth months. Probability at least two people have the same birth month is, so we need to find p of n, and then we can find 1 minus p of n. Okay, the first person does not match any birthday of somebody already in the room. Probability of the second person matching the first is 365 out of 366. Because the second person has a different birthday when he or she was born on one of 365 days other than the first person was born. The probability of the third person, okay, so this is where the answer to part B came from. So to determine the minimum number of people in the room, so the probability of at least is greater than a half, we use the formula we have found for 1 minus p of n. Okay, so that's where this comes in. All right. Okay. So 1 minus, so 11 over 12 times 10 over 12 times let's do 9 over 12. So this would be n equals 4, 13 minus 4 equals 9. All right, I'm going to stop my share right quick. Let's run these numbers right quick. So actually, I'll go ahead and share my screen again. This is what I'm going to be punching in. I think this should be one number too short. Okay, I'll share my screen. So it's going to be 1 minus, and then 11 divided by 12. Okay, that's 0.08. So if n is 1, or I'm sorry, if n is 2, then 0.083 repeating. For n of 3, Zero 0.2361 repeating. Okay, so whoops, times, so for n of 4, it's going to be 0.427083 repeating times 8 over 12, and that's going to get us 0.618 0.055 repeating. Okay, so we'll pop back here and we'll pop to our odds. And 19C, we see that N needs to be 5. Because somewhere in here is a probability of 1/2. So I'm gonna stop my share right quick so you can see my math. So anyway, I was just running this through Google. So this would be a case of 2, 3, 4, and then 8/12 for 5. Okay, so the answer to that question is we need 5 people. Now, part of the reason why this is an important thing to realize is I want to call your attention to one other thing that's going to make this more important. I'm going to get rid of this for right now. There it is. One of the things that's coming up is this little exam, and it says, write a program to demonstrate the number of people needed to ensure the probability of at least 2 of them have the same day of the year, at least 70%, 80%, 90%, 95, 98, and 99. Okay, so this is going to lay heavily on this little discussion right here. So hint, use example 13 from 7.2. We need to put that in there. Hint, use example 13 from 7.2. All right, friends, I'll go ahead and stop there. Thank you all for your time. Please let me know if you need help with anything else. Take care.